Question 3. This is the reaction between the halogenal alkane with hydroxide. So 2-bromo-2-methylpropane used, and this is the tertiary halogenal alkane. After it reacts with hydroxide, it will form this tertiary alcohol, and the bromine has been substituted by the hydroxide. Okay, and now bromide will be the leaving group. Okay, this reaction use phenolphthalein as indicator, and the stopwatch started as soon as the substance mix. Okay, then the reaction stopped when the pink color disappear, which means all the hydroxide used up. When all the hydroxide is not there, then the pink color will disappear. And for this question, it has 3 different temperatures. 20 degrees C use 300 seconds. 25 use 65 seconds. 35 degrees C use 20 seconds. So from here we know that when temperature is higher, rate is higher. Okay, explain what it means by the terms rate of reaction. Very easy. Change in the amount. Amount means the mole, okay, of the substance with time. In the graph show, this graph, the distribution of the molecules in the sample of 2-bromo-2-methylpropane. EA represent the activation energy. Okay, part 1. Label the graph to show proportion of the 2-bromo-2-methylpropane molecules which have sufficient energy to react. So it's actually this part. Right, so you just label as part 1. Use the same axis to sketch the distribution of energy of the molecules in a higher temperature, 50 degrees C. So you just try to draw a dotted line. Okay, so make sure it's to right and lower. To right and lower. So therefore, here, if you have more molecules able to undergo successful collision, and the rate is higher. Okay, state the effects of an increase in temperature on the EA. Okay, the EA, as you can see here, the EA, even higher temperature, the EA still same. It won't change. EA will change when we use a catalyst. So if you lower the EA, means it's going to move to left on the graph. Okay, therefore answer is no change because no catalyst used. Okay, part C1. Draw the mechanism to show the reactions between 2-bromo-2-methylpropane with hydroxide. Okay, so this one is the tertiary haloalkane, so it will undergo SN1. SN1, it must undergo bond break first. So means the CBr bond break, and of course you must put the dipole, partial positive on carbon, partial negative on bromine. Then you show the CBr bond break. Okay, the arrow must from the CBr bond point to bromine. Then you get 1 mark. After that, correct intermediate also important. Carbocation ion will form, and the hydroxide, you must show the lone pair on oxygen, and the arrow must from the lone pair point to the carbon or the carbocation ion. So it shows that it's going to form new bonding, new CO bond. So it will form this product. Okay, the product and the bromide. Okay, name the mechanism for this reaction. When they ask name the mechanism, what is the mechanism name or what? So you have to give a specific one, not just substitution. The name of this mechanism is nucleophilic substitution, because nucleophile used to substitute the halogen, right? So we call nucleophilic substitution. Okay, D. The original experiment is repeated at 25 degrees C with 2-chloro-2-methylpropane. So instead of 2 bromo, now we use 2 chloro. Okay, so we know that the CCl bond is much stronger than CBr bond. So CCl bond is hard to break. Hard to break means it needs more energy. EA is higher. That's why the compound or the reaction with this compound, this will be slower. So what we can predict is the reaction will take longer time because the CCl bond is stronger than CBr bond, higher EA. Okay, that's all for this question. Thank you.